you go. Testing, hello. All right, if you're watching from home, you'll want to open up It's Learning. There's something called Lecture 1, Lecture Quiz 1, underneath the first unit there, the Intro to Earth Space, and there's a question in there that you can fill out while we go through this lecture. So it's going to be about Earth's differentiation and the formation of Earth, the nebular hypothesis. So we'll talk about that as we go, and it'll be easy to fill out if you've got it open. Okay, here we go.
Geographers study the Earth and design maps to illustrate important information about the land and how it is used. What are some important tools and symbols found on maps? From space, planet Earth looks like a blue and white spinning marble. Take a closer look. Now you can see oceans, continents, lakes and rivers. Then cities, buildings, and lots of people appear. Geography is the study of all these elements of the Earth. It is a way of understanding people and places. The most valuable tool for a geographer is a map. And there are many kinds of maps. Physical maps that show land and water features. Relief maps that show elevation, the height above sea level. Political maps that show country and state boundaries. Population density maps that show how many people live in an area. Maps that show vegetation. And maps that show weather patterns. So you see, the same place can be shown in many different ways. It all depends on the map. Satellite cameras scan the Earth and take accurate pictures of water, land formations, and weather. These images help geographers make accurate maps of the Earth's surface and weather patterns. On almost every map, you will see a compass rose that shows the cardinal directions of north, east, south, and west. The scale of a map tells you how the distance on the map relates to the actual distance on the Earth's surface. This map shows the major roads in the northeastern United States. 1 inch on this map is equal to 100 miles on land. Geographers divide the Earth into hemispheres, or half circles, northern and southern, and eastern and western. The United States is in both the northern and western hemispheres. Many maps are crisscrossed by imaginary lines. The equator is an imaginary line that divides the Earth into the northern and southern hemispheres. The prime meridian is another imaginary line. It runs from the North Pole to the South Pole and divides the Earth into eastern and western hemispheres. In 1884, a group of geographers decided that the prime meridian would run through Greenwich, England. To pinpoint an exact location anywhere on the Earth, geographers used the imaginary lines of latitude and lines of longitude. Lines of latitude measure the distance north and south of the equator. Each line is parallel to the equator, so they are called parallels. Lines of longitude measure the distance east and west of the prime meridian, so they are called meridians. These aren't natural lines you'll see in a picture of Earth from space. They are drawn onto maps to help us find locations. With so much information to show and so many ways to show it, maps are valuable tools for understanding the world around us.
All right. So, has anybody ever been south of the equator? No? It's pretty far away, like from us, right? I actually have been south of the equator. At least once. I was in New Zealand, and it was pretty cool because it's different because the further south you go, the colder it gets, and the further north you go, the warmer it gets. So everything's reversed. Like around here, if you head north, it's going to get cold, right? Head towards the pole. If you head south around here, it's going to get warmer. You're going to like head towards Florida, right? It's a complete reverse down there. And so it kind of messes with your brain a little bit when you're thinking about it. Like I was down in the southern tip of New Zealand, and there's penguins. And up north, it's like a rainforesty sort of stuff. So it's totally reversed. So we're going to dive in here, play the where do you think he loses that game, I guess. So anybody want to take a guess where that picture's from? Anybody ever heard of Giant's Causeway? No? Any Led Zeppelin fans? Houses of the Holy, elbow mark cover, all the weird looking naked babies lying all over the rocks. That's it right there. You know what country that's in? It's taken in Ireland. These are basalt columns. So this used to be underneath the ocean. All this rock used to be underneath the ocean. Millions of years ago, it was thrust back up, and now it's on dry land. And in fact, it continues out into the water. You can't see it in that picture there. It's very wet. It's raining that day. But these really cool columnar columns go out into the ocean and actually come back up again on land over near England. I think in Scotland, they come back up onto land. So it's like it used to be all connected, right? So this is ancient ocean floor that as the magma oozed out as lava, it cooled and then cracked into these weird, bizarre shaped things. And they're big, tall columns. I mean, some of them are so tall, like, you get way up on top of them, like whole like mountains of this stuff. It's really neat looking stuff. So what we're going to do today is mostly just kind of give this a little overview of this unit and of Earth space. Earth space science encompasses, oh my goodness, pretty much everything, right? Everything has to do with the Earth. Everything has to do with space. So our subject matter is pretty broad. We talk about a lot of things in here. We're going to talk about the planets. We're going to talk about the solar system. We'll talk a little bit about the universe. This is some pretty broad stuff. So big things that we'll discuss this year: geology, okay, which is the study of the geological features, the study of the Earth itself. Oceanography, we'll talk about the oceans. It's a big part of our planet. Meteorology, we'll talk about the atmosphere, the weather, all those processes. And then finally, astronomy. We'll delve into the planets and the universe. Okay, so this bit here is going to be what's important for part of your question. Okay, and you're welcome to write things down kind of as we go and kind of synthesize it in your mind. You're welcome to use some of the words that I have up here, that's fine too. So our planet Earth, okay, formed in a very similar manner that all the other planets in our solar system formed. Okay. And the hypothesis, which at this point really truly should probably be called a theory, because it has a lot of evidence backing it up, is that our solar system formed from a big cloud of rotating dust and gas. And we called this the solar nebula. So a nebula in space is just a big cloud of gas and dust. And in our region of space, all of this material began collapsing. Now this is a huge cloud of gas and dust. Where do you think most of the gas and dust went in our solar system? It's the biggest thing in our whole solar system. The sun. So almost all the gas and dust, as it collapsed, ended up inside of our sun. That's why it's so massive. All of the other stuff ended up in the planets and out further from the planets. Okay. So the nebular hypothesis, okay, is the hypothesis that our solar system formed from a big cloud of rotating gas and dust. We'll talk a little bit more about it here in a second. We could go into a bunch more detail about this. I don't know if we'll talk about it now, but well, maybe a little bit. Do you guys know what our solar system is inside of? What are we kind of in orbit around? Starts with an M. It's named after a candy bar. Actually, the other way around. We're in the Milky Way. And the Milky Way is our galaxy, and we're just one star among billions of stars, hundreds of billions of stars, inside of this gigantic structure that's rotating. Now, it just so happens that a big cloud of gas and dust collapsed, and there's lots of ways that can happen. One way is when two clouds collide. Another way is when a star explodes nearby. It can compress an area of gas and dust and then trigger more star formation. So that's what started forming our star, the sun, and then the planets were kind of like, it's almost like the leftovers from the star is what became the planets as it formed. So let's go a little bit deeper here. The nebular hypothesis tells us that this nebula, which is just gas and dust, was mostly hydrogen and helium. Now, what do you know about the elements hydrogen and helium? Are they heavy or are they light? They're very light, right? You breathe in helium and you talk really funny. You ever do that with a balloon? Right? Probably not good to do too much of that, but if you suck in air from a balloon, it's mostly helium, and then it changes the density of the air as you talk and you sound like, high little squeaky voice. It's pretty funny. It's very light stuff. And so this is primarily what our sun's composed of. And think about how hot the sun is. It has so much gravitational force that it holds all this stuff in. In fact, Earth's very first atmosphere was probably hydrogen and helium. And as Earth heated up, it didn't have enough gravity to hold on to those gases, and they did what any good helium balloon would do, and they floated off the Earth, like literally boiled off the Earth. And now our atmosphere is mostly nitrogen, oxygen, things like that. So all of this happened about 5 billion years ago. Roughly 5. It's about 4.6 to be more exact. Sometimes people say 4.5. A billion years is hard to imagine. It's a long, long time ago. And that's when the formation of all the planets. So if you date any planet in our solar system, excluding our moon is a little bit different, but if you date all the planets, including the sun, you should come with a date of around 5 billion years. That's when it all started to form. Now the Milky Way that we're inside of is much, much older than that. In fact, it dates back to not too long after the Big Bang. Billions and billions of years ago. So it's an old, old thing. So it's assumed that as our solar system contracted, so picture all this gas and dust falling towards the center of this thing, it's going to become our sun, it began to rotate. Maybe we'll demonstrate this later, but it's kind of like if you've ever seen an ice skater who's doing one of those twirly things on one foot, what happens when they bring their arms in? They speed up a lot. And when they want to slow down, they let them back out. I've tried to do that before. It doesn't usually end well for me. Usually I crash. But somehow they manage to stand on one foot, spin around, and pull their arms in, and they speed up. So if you imagine, everything in space has some sort of motion. Everything's moving one way or another way. And as things start to fall inwards, it speeds up. So this whole cloud starts to rotate really fast. Ever wonder why all the planets go around the sun the same direction? This is part of our hypothesis right here, is that they formed that way because everything was going that way. In fact, even our sun, and you may not know this, our sun rotates on its axis. It spins like Earth spins on its axis, which gives us day and night. The sun, it doesn't, it's the sun, so it doesn't have day and night, but it rotates on its axis in the same direction as all the planets. Now there's some oddballs out there. We'll probably talk about them some, but this caused this thing to flatten kind of like a pancake. That's why our solar system looks kind of flattened in one direction, with all the planets going around it. Everybody good on that one? Good. Okay. So the inner planets are known as the rocky midges, which is a funny word, because they're little midget planets, and they're all rocky. Mercury, Earth, Venus, Mars, they're all rocky. You could stand on them, right? You couldn't breathe, but you could stand on them. And some of them you'd be melted. But the inner planets are all like hard and rocky. They have metallic cores. The core of our Earth is nickel and iron. Okay? The outer planets are much, much bigger. And they're known as the gas giants because they're mostly gas and ices and things like that. So if you think about this, it makes sense with the hypothesis. If this big hot ball, right, called the sun is in the middle, all of the really, really light stuff is going to get blown out to the further reaches of the solar system. So the further planets are much bigger, and they have all these gases that are too light to exist in the inner solar system. And all the inner planets are kind of small clumps of rock. Okay, that's essentially in short, the nebular hypothesis. Now it makes sense, because nebula is a word for cloud of gas and dust, and it contracting is the cause of the formation of our own planet. Okay, here's a picture of that. There's the nebula, big cloud up there, letter A. It begins to contract, it flattens, the sun begins to form, a little protostar. The sun ignites nuclear fusion, blows off its cloud of gas and dust, and we've got planets on the inside, planets further out. There we go. Let's talk about the second part of that question on your quiz. So, if that's how the planets formed, and that's how the solar system formed, through the nebular hypothesis, how did the Earth come to look the way that it does? And it's not exactly like the nebular hypothesis, but there's some similarities. The Earth differentiated, and that's the word I used on the quiz. And what happened was that the early Earth was molten. It was like, think of it as a liquid ball of rock. Okay, I mean, it was liquid. So, you know, when you think of the heavier elements on the periodic table, nickel and iron are up there. That stuff's pretty heavy, right? It's dense. So those things actually sunk to the center of our molten Earth. Right? So all the heavy stuff sunk, and all the lighter stuff floated to the top. So I'm trying to stand over here by my computer so that people can hear me. The heavy stuff sunk, and the lighter stuff floated to the surface. That's what differentiation means. Otherwise, it'd just all be mixed up, right? Now, this is actually a good thing for us. It's a good thing because where do things like plutonium and uranium fall in the periodic table? Are they close to the bottom or close to the top? Anybody know? They're near the bottom. They're really heavy elements, and they're all radioactive. So that means, like, you couldn't walk around on a uranium ball if that was your planet. So all of the uranium, all of the heavy stuff, it all sunk to the middle of the Earth. Ever wonder why we have volcanoes and things like that? It's because the core is still super duper hot. It's radioactive. And there's other reasons it's hot too, but it's releasing all this energy because all that stuff sunk down there to the core. Now, what's our rock on the surface made up of? Silicates, oxygen. It's materials, it's elements that bond together to make rocks that are super light. You can almost think of it like all of the like really heavy metallic stuff sunk, and all of the scum floated up to the surface, and that's literally what we walk on and what we're made out of. Now it's good because that scum that floated to the surface has carbon and oxygen and all the stuff that we need to live, but it is all the light stuff that just floated up to the top. And as the Earth hardened, that's what we got for our surface. And of course all the gases escaped and became part of our air. So right there we've got the formation of our atmosphere, formation of the core of the planet, and all the other layers. You don't have to list all those. And the formation of our surface. So there's some similarities between that and the nebular hypothesis, right? But this is known as differentiation. The different layers of Earth formed this way. Okay, anybody have any questions about that one? You can still keep writing if you're still working on it. All right, here we go. Let's go back a little further in time. This is a really quick, broad overview of the Big Bang Theory. So, the idea behind the Big Bang Theory, and this is super brief and in short, there is a tremendous amount of more information I could tell you about this, but all of the things in our universe, everything, came from the original Big Bang. In fact, what's really weird about this is that it didn't exist somewhere in space, which is a misconception. It's everywhere. It is space. We're inside of it. So if you want to ask the question, where is the Big Bang? Where did it happen? Like, where was it located? We usually plot things, latitude, longitude. We can locate anything on the Earth. It's not like that for the Big Bang, which is confusing for folks. It literally happened everywhere. In fact, you're it. You are part of it. And it's continuing to happen right now. In fact, the whole universe is expanding, and you're part of that expansion. This is some weird stuff to wrap your head around. I don't want to get too much into it. But as the universe cooled, it started out from an extremely hot and dense state, and it began to cool. Gases formed, protons, neutrons, elements formed, the galaxies began to form. Within those galaxies, individual stars were forming. Around most of those stars, we'd assume probably the majority of those stars, planets formed, right? Somewhere in there is Earth. In fact, our galaxy is just one galaxy of many galaxies, roughly about a dozen that are in our local area. We call our local group, and they're all orbiting around each other. It's really weird. In fact, someday in the distant future, millions of years from now, the Earth and our sun, which will be burned out by then, which is in the Milky Way, will collide with the Andromeda galaxy, which is a very similar galaxy to ours. It's very large. Our galaxy is huge. Both these two huge spiral galaxies are going to collide. Now, the stars in any individual galaxy, even though there's billions upon billions of stars, are so far apart that none will actually hit. Imagine that many stars just passing right past each other. Now, the gravitational effects will be something else. Some stars will be ripped off with their planets and chucked out as rogue planets out into space. Some stars will be stripped off with their surrounding planets and be pulled into a different galaxy. The merger is going to be pretty interesting, pretty spectacular. None of us will be here to see it, unfortunately. So, let's look at some of the spheres. We've already kind of mentioned some of these. The hydrosphere involves all the water on our planet. It's a very important part of our planet. Any astronaut would tell you this. From the space station, the majority of Earth is water, right? We have a water planet. It's striking when you look at it compared to the other planets. Most of our water is in our oceans. There's a significant part of it locked up in glaciers. Most of our water isn't fresh. You can't drink it. Right? But nearly 71% of Earth's surface, that's a lot of water. Oops. Yeah. We have our geosphere. Oh, atmosphere and biosphere. Sorry, in the wrong spot. The atmosphere is that thin blanket of air. You think of the atmosphere, the air, as this big thing, but it's very thin. It's like if the Earth was an apple, the skin would be the air. That's how thin it is. So when you see SpaceX launch something into space, it really doesn't have that far to go. It's very hard to get up there because of the gravity, but to get to space isn't that far away. A couple of kilometers, it's not very far, right? The majority of our air is below about 5.6 kilometers, which means if you climb up Mount Everest, you eventually get to a point where you can't breathe anymore because there's no air. You're nearing the edge of the air, and eventually you'll be in space. Right? If you kept going further than Mount Everest, you won't float off the mountain and end up in orbit or anything. That'd be kind of fun. If we had something that was tall enough, you could just climb up to the top and take a jump, and then all of a sudden you're in orbit. Yeah, some space elevator. I'd do it for sure. Would you guys go to Mars if it meant you couldn't come back? Yeah, I don't think I would. If I couldn't come back, I don't think I would, because I think it would get pretty boring after a while. But it'd be pretty neat to see, for sure. So the biosphere is biology, essentially. It's all the life on our planet. A tremendous amount of that's in the oceans. The geosphere is all of the hard, rocky parts of our planet, going from the core, the mantle, which is in between, big section, the crust, the scum on top that we're all made out of. Here's a picture of that. A little bit better, you can see. The inner core, think of these as spheres. The inner core, the outer core, the mantle, the upper mantle, and then the crust. And we'll talk some about plate tectonics in here and how that stuff moves. But roughly speaking, the layers of the Earth, the inner core is solid, liquid nickel and iron, nickel and iron. The outer core is actually liquid, which is weird. Okay. liquid nickel and iron. The mantle is solid. It's a little bit lighter than the stuff in the cores. And then the upper mantle starts to get a little plasticky, almost like silly putty. And then the crust is pretty hard and rocky. But there's some differences between all this stuff. Enter our theory of plate tectonics, which is the idea, the concept that the Earth is a whole bunch of, looks kind of like a cracked eggshell. And there's these plates that consist of the crust with a bit of the upper mantle, and they float around on this stuff called the asthenosphere. And when plates collide or pull apart, that gives us volcanoes and earthquakes and all these weird geological things. I think there was just a big earthquake someplace weird. Someplace out east, wasn't it? I don't remember. I just heard about it. I can't remember where it was at. I remember it being kind of like surprised, like there wasn't any plate tectonics out there. We have a fault here near Indiana, the New Madrid Fault. Have you guys ever experienced an earthquake in Indiana? We do have them. They're usually pretty, not real high on the Richter scale. They're pretty easy going when they hit Indiana. But down near the fault line, it can level cities. It's not too far. The New Madrid fault line is not too far away. But yeah, there have been some big ones in the past. I remember a few in Indiana where I woke up in the middle of the night because I thought like a train was going by. Kind of sounds like that. My bed was shaking. Things were falling off the walls. It's pretty freaky, especially if you're in Indiana. You're not used to something like that happening. If you live in California, like that starts happening, you're like, oh, okay, it's time to get underneath the desk and hide, try and get out of the building. But around here, it's a little different. So we determine location on our planet with latitude and longitude. So there's these lines on the globe, okay, that run north, south, and east, west. And you can plot any location on a sphere with that. So we're going to do some of that in here as we go. Latitude are the north-south lines, so they go like this, and longitude are the long-running lines from the poles. Okay. I think the video told you guys a little bit about how we chose that, which is interesting. Like, it's easy to pick a line to make 0 going this way. Well, you pick the line right in the middle, right? And that's the equator. That's the easy one. But pick a line going north-south that's 0. Well, that's a little more difficult because, like, there's no special feature. So what scientists did is they got together and they said, hey, let's make it Greenwich, England. Now, why? Because a lot of famous science happened there. It's a famous location. I think it's where the site of the world clock is. So they just randomly picked a spot, and they said that's 0. So you got to have somewhere. So we'll talk about maps a little bit in here. We will mess, hopefully, a little bit with some topographic maps, my favorite maps. On a topographic map, and I think this might be a question on the test, is that the contour lines, which are the lines on the map, are lines of equal elevation. Have you guys ever seen lines like that on a map? Have you ever seen a topographical map? I know you guys are used to using Google Earth and Google Maps to find things like drive your car and whatnot, but if you navigate in the wilderness, if you go into the back areas of the world where Google Maps does not work, you have to be able to read a topographical map. In fact, when I'm racing, I do adventure racing. I have to read these maps to figure out where I'm going at high speed. Sometimes like at 2-3 a.m. in the morning without any sleep, just continuing on and on trying to read these maps. It's super duper fun, but it's easy to screw up. These lines are lines of equal elevation. So if I'm standing here, it might be 100 feet above sea level. And this one might be 120 feet above sea level. So what would this feature be? Anybody want to guess? What would this be up here? Yep, this would be the top of a hill. Okay. So you can read that, and visually in your mind you can see what is happening on the map. It's a pretty cool thing. Lots of things in our planet are systems. We have open systems, we have closed systems, right? An open system is a system that lets energy and matter come in and out, okay? And in many respects, the Earth is an open system, right? Energy from the sun comes in, we lose heat out to space. A closed system is completely contained, like our engine cooling system in our car. The coolant shouldn't be getting out, right? It should stay inside. I've got a completely self-contained system over here. This is an ecosystem in a jar. So these poor little buggers live in here, whatever's living in there right now, has been sealed in here for like 13 years. So whatever air is available in there, whatever oxygen is available in there, comes from the plants that are growing in there. And the animals produce carbon dioxide that the plants recycle, but they don't get any new stuff. They're just sealed. Now the sunlight gets in, so there's that. But this is it's about as close as you get to a closed system. Nothing in, nothing out. Whatever's in there is stuck in there. So we'll see that some parts, I'm going to close that because it's hot. Some parts of our planet are closed systems, other parts are open systems. It depends kind of what you're talking about. But they work together in some very complex ways. Yep. Subsystems, yep. Where does our energy come from? This is a good question. And I know a lot of you think about this one. You've heard this in biology. The sun drives almost every process on our planet. We would not have wind if the sun didn't exist. It'd be very cold, of course, right? We wouldn't have life if the sun doesn't exist, because the plants capture the energy from the sunlight, they make sugar, and we eat sugar by killing the plants, or we kill animals that ate plants. But all the energy that makes us move around, that does anything, ultimately comes from the sun. But there's another energy source that runs a lot of stuff on our planet we don't usually think about, and that's all that heat that's down there inside of the core of the planet. That's what's making the mountains, that's what's making the volcanoes, that's what's making the earthquakes. It's not insignificant. Now, will that heat last forever? Oh no. Eventually, Earth's core will cool off. And when the core cools off, parts of the rock cycle will stop. And the potential for life on our planet will be pretty low. Because this part of the life on our planet requires rocks to be recycled, in the phosphorus cycle. So we'll talk more about that later, but that's the leftover heat from formation. That's the leftover heat from radioactivity, from bombardment, all sorts of things. Yep, we're part of this system, right? We're a part of the whole process. Of course, we interact with our environment, right? And we'll study all the different landscapes and environments of our planet. We'll talk about resources on our planet and resources that are renewable versus non-renewable. I know you've heard this before. But renewable resources are things we can get more of in our lifetimes. In human scales, that's what we care about. Non-renewable things are things that we've only got so much. There's only so much fossil fuel on our planet. It doesn't replenish. It does, but on a time scale humans care about. We don't have time to wait around 100 million years. Nobody's got time for that. Metals, right? We only have so much of it. Think of it, most of it's sunk. Anybody want to guess where all the metal came from? If almost all of it sunk to the core, how do we have desks and chairs and knives and things? Computers. If the earth was liquid and it all sunk, somehow we had to get new metal on the surface. So most of the metal on our surface that we use very likely came from asteroid impacts after the earth had cooled. So rocks from space brought us interesting stuff like this. In fact, a lot of our water came from rocks from space, as well as outgassing from volcanoes. But that's a whole different story. Population, right? It's a very important part of all this. Understanding how fast humans are growing. It's a little frightening. It's a little old graph, but yeah, that's some exponential growth right there, right? We're well over that right now. And that has to do with a lot of things. Larger populations mean more disease, right? Larger populations mean less resources. In fact, I was reading a scientific article just the other day about viruses, and they were looking back at human history and trying to determine, how virulent, how dangerous viruses were. And it's interesting to think about it in terms of this, but viruses evolve. They change through time, just like any living thing does, even though viruses aren't considered alive. Well, they were looking at the transition when humans went from being hunter-gatherers, you kill it, you dig it, you move in your little roaming band, you're living in small groups, to when humans went to farming, agriculture, and then civilization as we know it. And come to find out, viruses actually got worse when humans moved into larger groups. Because for a virus, and remember, viruses don't think about these things, viruses can't be so deadly that they kill their host before they can spread to the next host. Otherwise, the virus is gone. It's wiped out. So in a small population, viruses can't be very deadly. Otherwise, they're done. If they kill the first person they infect and that person doesn't infect anybody else, it's over. But in a large population, a virus can be much more deadly because the chances of spreading are so much easier for the virus. Now, the virus doesn't think about all those things. It's just a fact of biology, right? It's interesting to consider that, though. Okay, environmental problems, right? All the air pollution, other things we'll look at, some of the hazards, earthquakes, landslides, acid rain, global warming, ozone depletion. We'll try and talk about some of those things. We make assumptions in science. We talked a little bit about that the other day. We assume that the universe is predictable, it's consistent. The measurements we make here would be similar to measurements we could make anywhere in the universe, right? Gravity behaves the same way. And our goal in science is really to discover, predict, and make models of the universe, make models of the world. Whether it's our Earth or the weather systems or the geology, we model things in science. That's pure science. Scientists don't necessarily exist just to make new things for us to play with or to save our lives. It's really about making a model of the world and figuring out how we can use that stuff. Enter hypothesis and theory. We talked about this a little bit before. We mentioned hypotheses. A hypothesis can become either a theory or a law. Those things are on equal footing. A theory doesn't ever just become a law. Okay? But those are well-supported hypotheses. And we use the scientific method, right? Gathering facts, coming up with hypotheses, testing them, rejecting them, going back over. We mentioned some of this the other day. Finally, we gain our knowledge of science through doing things like collecting facts, right? Developing a hypothesis, conducting experiments, re-examining that stuff, and then eventually publishing it so other scientists can take a look at it. Okay? All right. Anybody have questions about all that? Everybody got their question answered?